This one's amazing. All right, we've got a implicit curve here that they drew, and then they want the linear approximation, so we'll write the equation of the line in just a moment. And then, okay, when x is 1.5, what's the y? Okay, and then what's the error in that approximation? Okay, so this is cool. So the only new thing here really is that it's implicit. All right, so we will take care of that right now. All right, let's go. Let's go Pank. All right, so here we go. So the derivative of this will be 2x. Okay, and then plus the derivative of natural log is 1 over. So it'd be 1 over x over y, but I could just multiply by the reciprocal. And so that would be y over x. Okay, so y over x. And then times, we'd have to do a chain rule. So the chain rule is going to be a quotient rule, all right, where a dy dx going to be embedded there. So it's all good, and so we'll clean it up here in just a second. All right, and so we're going to have a fraction, and of course your denominator is going to be y squared. All right, your numerator is bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is going to be y prime. I don't have a lot of room here, so I'm just going to put y prime. And we're going to solve this for y prime, and that equals 0. Okay, so then, all right, so we definitely want to get the derivative by itself. So let's do this. Let's subtract the 2x from both sides, and then multiply both sides by x over y to clear out that fraction. All right, so that'll look like this. So y minus xy prime over y squared. It's going to equal, now just kind of follow the algebra here, subtracting the 2x from both sides will give me a negative 2x, but then I'm going to multiply that by x over y. So I'll have a negative 2x squared over y. All right, so far so good. And that's going to lead directly to multiplying both sides by y squared, which will cancel out one of the y's on the bottom. So I'll have y minus xy prime is going to equal negative 2x squared. And then if I multiply by y squared, I don't know why I'm acting like I'm going to have a fraction here, times y. Okay, didn't need to have a thing like that at all. So then subtract the y. So I'm heading down here. All right, so I've got negative x y prime will equal, however you want to do this, I'll say negative y minus 2x squared y. Okay, which then leads to dividing by negative x, and I have it. So if I divide by negative x, I'll have negative, well, I'll put it at the end, negative y over x. I'm actually going to divide by negative x, so that's going to be positive. And then plus, and I'm dividing by negative x. I've already divided by the negative, and then that'll give me a 2xy. Okay, so this is y prime. All right, and what do I need to get the equation of the line? Not a lot, because they already told me over here that when x is 1, y is 1. All right, that's cool. By the way, to prove that, if I had a 1 right here, yeah, this is going to be fine. So if I put a 1 right there, if I had to do this algebraically, so I'd have 1, I'm just going to put a little note here, 1 plus the natural log of 1 over y, okay, equals 1. Well, then the 1s will cancel out, and I'll have the natural log of 1 over y equals 0. All right. And if you write what that means, this means the base is e, and the exponent is 0. Well, that's 1. and that would have to equal 1 over y, and the only way that's possible is if y is 1. Okay. All right. Now, they told us over here on the graph, but I wanted to go ahead and show it. So now, so what I need, I know that 1, 1's a point. So 1, 1 is a point, and I got that right there. And now I just need the slope. All right. So the slope, I'm just going to substitute 1 and 1 into both of these. So this is, so 1 here and a 1 here is 1. All right. So I will say this. Dang, y prime. Sorry. Y prime. All right. So y prime evaluated at 1, 1 equals 1 plus 2. So my slope is 3. So the slope of that line right there is 3. Man, you can just see it. It's perfect. All right. So the equation of that line then is y minus 1 equals 3 times x minus 1. Okay. And I'm just going to stick with this notation. And it says by using that tangent line, what's k? Okay. Well, I'm putting a 1.25 in for x. So y minus 1 would equal 3 times 1.25 minus 1. All right, which is equal to 3 times 0.25 or 0.75. Now this is actually k we're talking about here. All right, so the y, which is actually k, I'll go ahead and make that distinction right here. This is the k that we're looking for, is going to be 1.75. Okay, cool. All right, now, so, all right, and it says, all right, what's the error in that? Well, okay, the problem is then I would need to know 1.75 what the y value here is on this implicit graph. Okay, so that's gonna be a little bit tougher, but we'll be able to do it. So I need to know to find the error. Okay, it's going to be the absolute value of that equation, and I don't even know how to say that equation when x is 1.25 and y is unknown. Okay, so I've got to go back and do this a similar thing that I did up here to find out what that y is, so I can find out what the what value I need to use, because at 1.2, I don't know why I'm pointing at the screen like you can see it. At 1.25 x value, I need to know what the y value is, and then we're going to find the difference in it and the 1.75 that we found used in the line. As you can tell, our estimate was an underestimate. All right, so whatever the true y is going to be larger. Okay, so let's do a little bit of algebra here to find out. So let's do that here. I'll come back to this in a second. We know it's going to be minus 1.75. You can subtract those in any order you like. All right, but here we go. So it's going to be x squared. X is 1.25. So 1.25 squared. And then I had plus the natural log of, so plus the natural log of 1.25 over y. Okay. It's equal to, wasn't that right-hand side just 1? Yeah, the right-hand side's 1. Oh, sorry. All right, equals 1. Okay, so a little calculator help here. All right, so I know I'm going to go 1 minus 1.25 squared. All right, we know we're going to do that. All right, so that's equal to that amount. And then the natural log the natural log of 1.25 over y would equal that amount. So let's get to that point. Here we go. So the natural log of 1.25 over don't know is equal to negative 0.5625. All right, and what you do at this point then is you just say, okay, what does that mean? Well, that means that e to the negative 0.5625 would have to equal this 1.25 over y. All right, to solve this, all you got to do is just switch these two. Because if you're going to cross multiply, right? I mean, multiply by y, divide by the e, right? So that's what we're going to do. So, all right, so I'm going to do two things here. I'm going to do that calculation. I'm going to say 1.25, okay, divided by e to the negative, the answer I just got a second ago. All right, so check this out. So the answer I just got a second ago. All right, there we go. This is the actual y value. So then to find the error, I'm going to, so I could write that. I'm going to that a little bit of it. I'm going to write a little bit of it right here as much as I can. So it's 2.193 out of room, okay? Because an e was involved. It's irrational. All right, so then if I just take that and then subtract 1.75, I don't have to worry about absolute value because that's going to be positive. All right, and so I've got an error quite large of 0.444. All right, I'm just going to say that. So that error is 0.444. And there you go. All right, and so that's the error. And if you wanted to know the percentage of that error, which we haven't really done that at all, and I don't think you'll ever be asked that, I would just take that and divide it by the actual amount. So it's the difference over what it actually should be. And so what actually should be is the 2.193.8, and then you get a percentage. All right. So it's a 20% error, multiplying that by 100. But it didn't really say that. It just says calculate the error, the approximation, and it was 0.444. All right. Okay. So that's all for that one. And then we move on. Lesson 6 is going to be like the easiest thing we've done in a long, long time.